At first glance, the scene appears tranquil, almost ceremonial. A female praying mantis stands motionless among the stems, her body aligned with the vertical geometry of the vegetation, forelegs folded beneath her head in a posture that resembles contemplation rather than threat. The light filters through leaves and grasses, broken into shifting bands that move slowly with the wind. In this stillness, nothing suggests urgency. Yet the ecosystem around her is charged with tension, because courtship here is not a ritual of mutual trust. It is a negotiation conducted in the shadow of predation, where a single miscalculation can end not in rejection, but in consumption. For the male praying mantis, approaching a potential mate is one of the most dangerous tasks in the insect world. He is not merely attempting to attract a partner. He is entering the strike zone of a highly specialized ambush predator whose nervous system is tuned for speed, precision, and lethal efficiency. The female's raptorial forelegs are engineered to snap shut faster than the blink of a vertebrate eye, powered by muscular leverage and hardened spines that lock prey in place. Evolution has shaped her body to solve one primary problem: how to capture and subdue moving organisms with maximum reliability. The male, by contrast, is smaller, lighter, and structurally less robust. In ecological terms, he is not just a mate. He is prey-sized. This asymmetry defines everything that follows. The male does not rush. He waits, sometimes for hours, positioned at the edge of the female's sensory world. His compound eyes, optimized for detecting motion and depth through stereoscopic vision, monitor subtle changes in her posture. A slight shift of the thorax, a rotation of the head, or a repositioning of the forelegs can signal readiness to strike. The male advances only when the environmental context favors invisibility. When wind moves the vegetation, when light flickers unpredictably, when background motion masks his own. Each step forward is slow, deliberate, and precisely timed to avoid triggering the visual algorithms embedded in the female's brain. The praying mantis visual system is unusually sophisticated for an insect. It excels at judging distance and motion, allowing the female to calculate the exact moment when prey enters the optimal range for capture. This same system makes her exceptionally dangerous during courtship. Hunger intensifies this risk. A well-fed female is statistically less likely to attack an approaching male, not because she recognizes him as a mate, but because the energetic incentive to strike is reduced. A hungry female, by contrast, is primed to interpret movement as opportunity. Stress compounds this effect. Environmental pressures, such as limited food availability, competition, or disturbance, can elevate aggression, shrinking the margin for error to almost nothing. The male's strategy reflects this reality. He approaches from behind whenever possible, staying outside the direct frontal field of vision where the female's depth perception is strongest. His movements are segmented into pauses, mimicking the stop-and-go rhythm of swaying leaves rather than the smooth trajectory of prey. This behavioral mimicry is not conscious, but it is deeply encoded through evolutionary filtering. Males that moved too quickly did not reproduce. Males that failed to read the female's state were removed from the gene pool in the most literal sense. What remains is a behavioral algorithm shaped by countless lethal encounters, refined into a choreography that minimizes detection while maximizing reproductive opportunity. Even when physical contact begins, the danger does not disappear. The male mounts cautiously, aligning his body with hers in a way that limits her ability to reach him with her forelegs. His grip is firm but calculated, using specialized claws to anchor himself while avoiding stimulation that could trigger a predatory response. At this stage, mating is already underway, yet the threat remains constant. The female's nervous system does not switch from predator mode to partner mode. There is no clear behavioral boundary separating courtship from hunting. Both processes run on the same sensory hardware, the same motor pathways, the same reflexive circuits. In some cases, the negotiation fails catastrophically. Sexual cannibalism, while not universal across all praying mantis species or all mating events, is a documented and ecologically significant phenomenon. When it occurs, it is not driven by malice or abnormal behavior. It is an extension of the female's feeding ecology. The male represents a concentrated package of protein and lipids, resources that can be redirected toward egg production. From an evolutionary perspective, his consumption can increase the female's reproductive output, even as it ends his individual genetic journey. The paradox is stark. The act of mating can directly enhance the success of offspring while eliminating the father. Yet even here, the story is more complex than simple sacrifice. Studies have shown that males may continue to copulate even after severe injury or partial consumption, because the neural control of mating behaviors is distributed and resilient. Insects do not rely on centralized brains in the same way vertebrates do. Much of their motor control is managed by ganglia along the nerve cord, allowing certain actions to persist independently of the head. This decentralization means that reproductive success can, in some cases, continue despite catastrophic damage. The boundary between life, death, and function is blurred, revealing a physiological architecture that prioritizes task completion over individual survival. From the ecosystem's perspective, none of this is exceptional. The praying mantis is both predator and prey, shaped by selective pressures that reward efficiency over sentiment. Her role extends beyond individual encounters. As an ambush hunter, she regulates populations of flying and crawling insects, influencing community structure at the microhabitat level. Her presence alters the behavior of other species, creating zones of heightened vigilance and altered movement patterns. The male's risk-laden approach is embedded within this broader ecological web, where every interaction feeds back into population dynamics, energy flow, and evolutionary trajectories. Thermoregulation adds another layer to this scene. As ectotherms, praying mantises rely on external heat sources to regulate body temperature and metabolic rate. Courtship often occurs during periods when temperatures support optimal neural processing and muscular performance. Too cool, and reaction times slow, increasing vulnerability for both parties. Too warm, and metabolic stress can heighten aggression. The timing of mating is therefore constrained not only by behavioral readiness, but by the thermal landscape of the environment. Sunlit clearings, shaded understories, and transitional zones each create different risk profiles, subtly shaping where and when these encounters unfold. What makes this courtship so compelling is not its violence, but its precision. There is no excess motion, no wasted energy. Every pause, every angle of approach, every moment of stillness is a product of evolutionary negotiation between attraction and annihilation. Romance here is not a shared experience. It is a narrow corridor between survival and extinction, navigated through sensory acuity, environmental awareness, and behavioral restraint. In the end, whether the male survives is almost incidental from the perspective of natural selection. What matters is that the system functions. Eggs are laid, genes move forward, the ecosystem continues its cycles, indifferent to individual outcomes. The praying mantis does not symbolize cruelty or tragedy. She represents a world where reproduction and predation are not opposites, but overlapping strategies, woven together by millions of years of selection into a single, unforgiving design. The air above a sunlit clearing is never empty, even when it appears calm. Invisible currents slide over bark, stones, and leaves, carrying chemical traces, heat gradients, and the low vibrations of passing wings. In this layered atmosphere, male wasps claim space not by building walls or digging trenches, but by turning landmarks into signals of status. A protruding branch, a sun-warmed rock, the edge of a flowering shrub becomes a focal point, not because it offers shelter or food, but because it anchors visibility. From here, a male can be seen, intercepted, challenged. In the world of wasps, mating begins not with approach, but with occupation. Territory in wasps is not a passive claim. It is a performance maintained through constant movement, surveillance, and rapid response. A male patrols his chosen landmark in looping flights, tracing tight arcs that keep him within striking distance of intruders, while maximizing exposure to passing females. His wings beat at a frequency tuned for agility rather than endurance, allowing sudden accelerations and abrupt changes in direction. This is not aimless flight. Each pass reinforces ownership through presence, and each pause in the air is calibrated to conserve energy while remaining alert. The landmark itself becomes an extension of the male's body, a spatial amplifier that makes him harder to ignore and easier to assess. Females moving through the area do not linger without reason. They evaluate from a distance, reading the choreography of motion and control. A male that holds a landmark consistently signals not only physical fitness, but cognitive efficiency. He can navigate turbulence, avoid collisions, and respond to threats without hesitation. These traits matter because they reflect underlying neurological performance, sensory acuity, and muscular coordination. In evolutionary terms, territory becomes a proxy measurement for genetic quality, compressing complex biological information into a visible pattern of behavior. Rival males interpret the same signals differently. To them, a defended landmark is a challenge. Intrusions are rarely accidental. A rival approaches deliberately, flying into the defended airspace at an angle that forces a response. The escalation is immediate. Both males accelerate, their flight paths tightening into spirals and sharp turns that test reaction speed and spatial awareness. No stings are deployed. The sting, a modified ovipositor absent in males of most wasp species, is irrelevant here. Dominance is decided through aerial positioning, endurance, and intimidation, not through chemical weapons. These clashes are brief but intense. Bodies collide mid-air, wings brush, and the soundscape shifts from a low hum to a rapid abrasive buzz as wing beats synchronize and then break apart. Each contact carries risk. Damage to wings compromises flight efficiency, and a male that cannot maneuver precisely loses not only territory, but survival prospects. The fight resolves when one male breaks pursuit, veering away and abandoning the contested space. Victory is defined not by injury inflicted, but by persistence displayed. The winner resumes patrol almost immediately, as if the interruption never occurred. The ecological context shapes every aspect of this behavior. Temperature governs flight performance, dictating when contests are most likely to occur. In cooler conditions, muscles respond sluggishly, reducing acceleration and increasing the cost of sustained patrol. In excessive heat, metabolic stress shortens endurance and sharpens aggression, making conflicts more frequent, but shorter. The most intense territorial activity often emerges during thermal sweet spots, when energy expenditure yields maximum performance. These windows can be narrow, sometimes lasting only hours, forcing males into concentrated bursts of competition. Sensory adaptations underpin this system. Wasps rely heavily on vision, particularly motion detection and contrast sensitivity. Their compound eyes are structured to track fast-moving objects against complex backgrounds, allowing precise interception during high-speed flight. Olfactory cues also play a role, but in mating territories, visual dominance takes precedence. Chemical signals linger too long, diffusing unpredictably, while visual signals can be updated moment by moment. A male's presence is reaffirmed with every pass, every hover, every chase. Females entering these spaces encounter not a single male, but a dynamic hierarchy. Some landmarks are held consistently, others change hands repeatedly, reflecting local population density and individual condition. A female's approach can trigger renewed competition, drawing in nearby males who test the defender's resolve. The air becomes crowded, movement intensifies, and the landmark transforms into a three-dimensional arena. To an outside observer, it resembles chaos. To the wasps, it is structured evaluation, compressed into seconds of flight. Predator pressure adds another layer of tension. Birds, dragonflies, and larger insects patrol the same airspace, attracted by movement and sound. Territorial displays increase visibility, raising the risk of interception. This creates a trade-off between mating opportunity and survival. Males that patrol aggressively gain attention from females, but also from predators. Those that remain too cautious may survive longer, but fail to reproduce. Natural selection balances these extremes, favoring strategies that optimize exposure without crossing thresholds of vulnerability. The absence of stings in these interactions does not reduce their seriousness. Injury here is aerodynamic. A torn wing margin, a bent antenna, or accumulated fatigue can end a male's reproductive chances. These costs accumulate silently, invisible until performance falters. The battles may lack blood, but they are no less consequential. Each flight taxes energy reserves, Each chase depletes glycogen stores that must be replenished through foraging. Time spent defending territory is time not spent feeding, further tightening the energetic budget. From a broader ecological perspective, these territorial systems influence spatial patterns of wasp activity. Landmarks become hubs of movement, shaping pollination routes, prey suppression, and interspecific encounters. Wasps are opportunistic predators, regulating populations of other insects through hunting. The clustering of males around mating sites can temporarily intensify predation pressure nearby, altering local food webs. Even brief territorial contests ripple outward, affecting organisms that never participate directly. The evolutionary origins of this behavior lie in the balance between mobility and control. Unlike species that rely on fixed structures such as nests or burrows, male wasps operate in open air, where boundaries are fluid and ownership must be constantly reaffirmed. This selects for rapid assessment, decisive action, and efficient retreat. There is no room for prolonged stalemate. The sky does not permit it. Gravity, wind, and predators enforce swift resolution. What makes these mating contests feel like weddings fought in the air is not violence, but ceremony under pressure. Each patrol is a declaration. Each chase is a test. Each victory is temporary, contingent on continued performance. The landmark remains only as long as the male can hold it, and even then, it offers no guarantee. A stronger rival, a sudden temperature shift, or a passing predator can reset the hierarchy in moments. When mating finally occurs, it does so against this backdrop of instability. The act itself is brief, secondary to the long investment in territory and display. Success is front-loaded, earned through sustained control rather than prolonged interaction. Once completed, the system dissolves. The male may resume patrol, or he may be displaced, his role concluded. The landmark returns to neutrality, waiting for the next contender to claim it. In the wasp's world, romance is not a private exchange but a public contest, conducted in shared airspace and governed by physics as much as biology. It is shaped by wing structure, muscle chemistry, visual processing, and thermal constraints. There is no negotiation with a partner, only competition with peers and alignment with environmental opportunity. Status is not inherited or declared. It is flown, defended, and lost, over and over again, in a cycle as relentless as the buzzing air that sustains it. The open sky above a meadow carries a pattern that is invisible until it suddenly becomes crowded. Warm air rises from sunlit ground, lifting scents from flowers, resin, and soil, while wind shears these signals into long, drifting layers. Within this aerial architecture, honeybees assemble for one of the most time-compressed and unforgiving reproductive events in the insect world. There is no prolonged courtship, no negotiation of territory, and no second chances. Mating here is constrained by altitude, temperature, and time, and it unfolds in a narrow window where success must be immediate. The wedding has a deadline, and the cost of meeting it is fatal. Male honeybees, known as drones, do not patrol flowers or build nests. Their entire developmental trajectory is oriented toward a single moment in the sky. From the day they emerge as adults, their physiology, sensory systems, and behavior converge on one task: locating and intercepting a virgin queen during her mating flight. Drones gather in specific locations called congregation areas, suspended volumes of air that exist year after year in roughly the same places. These are not random swarms. They form above clearings, landscape edges, or subtle topographical features that channel air currents in predictable ways. The exact mechanisms that define these sites are still under investigation, but they appear to be shaped by wind patterns, visual landmarks, and chemical accumulation that together create a navigational attractor for drones across the surrounding landscape. Within these congregation areas, thousands of drones circle continuously, their bodies forming a loose three-dimensional cloud. The density fluctuates with weather and time of day, thickening during warm, calm afternoons when flight efficiency peaks. Thermoregulation governs everything. Honeybees are ectothermic at rest, but capable of generating heat through muscular activity, especially in flight. Drones rely on ambient warmth to reduce metabolic cost, and mating flights are timed to coincide with temperatures that allow sustained aerial pursuit without exhausting energy reserves prematurely. Below this thermal threshold, reaction times slow and muscle power declines. Above it, overheating and dehydration shorten endurance. The window for optimal performance is narrow, and evolution has tuned behavior to exploit it with precision. The queen's entrance into this space transforms the air instantly. She is larger than any drone, her abdomen elongated and heavy with reproductive organs, yet she flies with remarkable stability. Her arrival is detected first through chemical cues. The queen releases a blend of pheromones that cut through the atmospheric background, triggering an immediate response. Drones accelerate toward the source, their flight paths converging into a moving column that follows her trajectory. Vision now takes over, guiding high-speed pursuit as drones attempt to position themselves directly behind her, where aerodynamic slipstreams reduce energy expenditure and maximize interception chances. This is not a gentle chase. The queen does not slow or accommodate. She flies decisively, forcing drones to match her speed and maneuvering through the air with abrupt changes in direction. Only the fastest and most neurologically responsive individuals remain in contention. The rest fall behind, their fuel reserves depleted, their chance gone. The congregation area, once crowded, stretches into a thinning tail of exhausted bodies drifting back toward the ground. When mating occurs, it is instantaneous and irreversible. A successful drone aligns with the queen mid-air and transfers sperm using an endophallus that averts explosively under pressure. This structure is not designed for reuse. The act ruptures the drone's abdomen, detaching part of his reproductive organ inside the queen. Within seconds, he loses control, falls away, and dies. There is no recovery phase, no retreat. His reproductive success is total, and his survival is irrelevant. Evolution has engineered a system where the completion of the task is the endpoint of the individual. The queen, meanwhile, continues her flight. She mates with multiple drones over the course of one or several flights, storing sperm in a specialized organ called the spermatheca. This reserve will last her entire life, sometimes several years, allowing her to fertilize millions of eggs without further mating. Genetic diversity within the colony is generated not through repeated pairings over time, but through this brief, concentrated sampling of the drone population. The consequences ripple outward. Colonies with higher genetic diversity exhibit improved disease resistance, more flexible division of labor, and greater resilience to environmental stresses. The drone's fatal contribution underwrites the long-term stability of the superorganism. From an ecological perspective, this system reflects an extreme division of labor. Drones do not forage, defend, or contribute to colony maintenance. They are fed and maintained by workers until maturity, representing an energetic investment with a single possible return. If they fail to mate, their value drops to zero. As seasons change and resources become scarce, drones are often expelled from the hive, denied entry, and left to die. This is not punishment, but resource management. The colony reallocates energy toward overwintering survival, eliminating individuals whose reproductive window has closed. Predation pressure shapes the mating flight as well. Birds and aerial insects exploit the density and distraction of drone swarms, intercepting individuals during pursuit. The queen's speed and altitude offer some protection, but drones are highly visible targets, their flight paths predictable once they lock onto a pheromone plume. Mortality rates are high even before mating occurs. This further amplifies selection pressure, favoring drones with superior sensory integration and reaction speed. The race is not only against rivals, but against the environment itself. The architecture of the drone's body reflects this specialization. Large compound eyes dominate the head, particularly in males, providing enhanced visual resolution for tracking fast-moving objects against the sky. Antennae are packed with olfactory receptors, tuned to detect minute concentrations of queen pheromones. Flight muscles are oversized relative to body mass, optimized for short bursts of high-intensity activity rather than endurance. Everything about the drone points toward a singular evolutionary gamble. What makes this mating system so stark is its lack of ambiguity. There is no behavioral negotiation, no assessment phase, no opportunity to retreat and try again. The drone's life trajectory narrows toward a single aerial moment, and when it arrives, the outcome is binary. Either his genes pass forward into the future of the colony, or they end in the air where he falls. Survival, in this context, is not a goal. It is a delay. The queen's role is equally constrained, though less visibly fatal. Her mating flights expose her to predators, weather instability, and navigational risk. Failure to return means the collapse of the colony's reproductive future. Yet she cannot mate within the hive. The open air is essential, allowing genetic mixing across colonies and preventing inbreeding. The risk is unavoidable, and evolution has balanced it against the enormous payoff of a successful flight. This is not romance shaped by mutual survival. It is reproduction distilled to its most efficient and ruthless form. Success is everything, because it is the only thing that matters. The drone's death is not a flaw in the system. It is a feature, ensuring that no energy is wasted on individuals who have already completed their function. The honeybee colony persists, not because individuals survive, but because roles are executed with absolute precision. In the end, the sky empties again. The congregation area dissolves, leaving no trace of the event beyond stored genetic material and the silent absence of those who succeeded. Below, the hive continues its routines, indifferent to the aerial losses that secured its future. The wedding is over. The price has been paid. Evolution moves on, carried forward by a queen who now holds the combined legacy of thousands of lives that ended so that hers and the colony's could continue. The forest floor does not announce what it is about to release. For weeks, sometimes months, a leafcutter ant colony operates with mechanical precision beneath the soil, harvesting fragments of vegetation, cultivating fungal gardens, and maintaining a living infrastructure that rivals small cities in complexity. Trails pulse with traffic, chambers regulate humidity and temperature, and waste is carried away to designated dumps to prevent contamination. Everything appears stable, optimized, permanent. Then, without warning to an untrained eye, the colony shifts its purpose. Reproduction is no longer a background process. It becomes the event. This is not a wedding between individuals. It is a coordinated dispersal of futures. Inside the nest, environmental cues accumulate. Soil temperature stabilizes after seasonal rains. Humidity rises to levels that protect delicate wings, and barometric pressure settles into patterns that signal safe flight conditions. The colony responds as a single organism. Special chambers open. Winged males and virgin queens, produced only during specific reproductive windows, begin to surface. They are larger than workers, heavier, their bodies shaped not for labor but for transport. These elates represent years of stored energy, converted into muscle, fat, and reproductive tissue. The colony has invested heavily, and it will not hedge its bet. When the mating flight begins, the ground seems to exhale. Thousands of winged ants erupt from nest entrances, spilling into the air in dense, chaotic streams. Predators are already waiting. Birds sweep low, lizards dart forward, spiders emerge from burrows. Mortality is immediate and extreme. From the colony's perspective, this loss is expected, even necessary. Producing excess ensures that at least a fraction will escape the gauntlet. Individual survival is irrelevant. Statistical success is everything. In the air, leafcutter ants become part of a regional event. Multiple colonies release elates simultaneously, flooding the sky with genetic material from unrelated lineages. Mating occurs mid-flight or shortly after landing, brief and efficient. There is no courtship ritual, no prolonged assessment. Compatibility has already been decided by colony health, timing, and environmental alignment. Once mating is complete, the partnership dissolves permanently. Males die soon after, their role exhausted in minutes. Queens, now fertilized, descend to the ground carrying everything they will ever need to begin again. What follows is not escape, but isolation. The newly mated queens land in hostile territory. The forest floor that once supported a thriving superorganism now offers no protection. Other queens are everywhere, all seeking the same scarce resources: suitable soil, manageable moisture, and freedom from competitors. Encounters are frequent and violent. Queens that meet do not negotiate. They fight with mandibles and body weight, grappling until one is incapacitated or killed. This is not aggression born of scarcity alone. It is selection in real time. Only one queen can claim a site. Any tolerance would doom both to starvation or fungal failure. Even after a queen secures a location, the transformation is not complete. She sheds her wings, snapping them off at specialized joints. These wings will never regenerate. Their muscles are broken down and reabsorbed, converted into metabolic fuel. Flight is over. The rest of her life will be spent underground. This act marks a permanent shift from dispersal to construction, from mobility to entrenchment. Love, such as it existed, has already done its work. Now comes empire. The queen digs alone. Her first chamber is small, shallow, and vulnerable. She seals herself inside, cutting off contact with the outside world. Oxygen levels drop. Carbon dioxide accumulates. Temperature and humidity fluctuate wildly compared to the regulated environment of her birth colony. Survival depends on physiological resilience. Leafcutter queens are uniquely adapted for this stage. Their bodies carry internal reserves of lipids and proteins sufficient to sustain them for weeks or months without feeding. More critically, they carry a fragment of their mother colony's fungal symbiont, stored in a specialized pocket in the mouthparts. This fungus is the true foundation of the leafcutter empire. The ants do not eat leaves. They cultivate fungus that digests plant material into a form they can consume. Without it, the colony cannot exist. The queen carefully deposits the fungal pellet, tending it with obsessive precision. She fertilizes it with secretions, protects it from contamination, and regulates the chamber's microclimate through posture and excavation. Her entire reproductive future depends on this living culture surviving its first vulnerable days. During this founding phase, the queen is immobile and exposed. Parasites infiltrate soil. Pathogenic fungi lurk in organic debris. Flooding can drown the chamber. Predators that burrow can breach the walls. There are no workers yet to defend or repair. Every risk is magnified because there is no redundancy. Failure here does not mean reduced output. It means extinction of that lineage. If the fungus takes hold, eggs hatch. The first workers emerge undersized and fragile, their development constrained by limited resources. They immediately begin tending the garden, expanding the chamber, and foraging cautiously near the surface. The queen never leaves. Her role narrows to continuous egg production, sustained by food processed by her offspring. The colony begins to scale, slowly at first, then exponentially. What was once a solitary insect becomes a reproductive engine producing millions. Seen from a distance, this process resembles inevitability. Leafcutter ants dominate landscapes, shaping vegetation patterns, influencing soil composition, and redistributing nutrients on a massive scale. Their colonies can persist for decades, expanding through underground networks that span hundreds of meters. But this dominance is built on a reproductive bottleneck so severe that most attempts never reach maturity. For every successful queen, countless others die nameless in the leaf litter. Ecologically, this strategy makes sense. By synchronizing mating flights across regions, leafcutter ants overwhelm predators and maximize genetic mixing. By forcing queens to compete violently after dispersal, they ensure that only the most resilient individuals establish colonies. By tying survival to fungal symbiosis, they lock their fate to a system that rewards careful management and punishes error. This is not romance as cooperation. It is reproduction as conquest. There is an irony embedded in the scale of it all. The largest ant societies on Earth begin with an act of extreme solitude. The queen's first weeks are spent alone, sealed in darkness, surrounded by the echoes of violence that eliminated her rivals. The love that initiated this process is already gone, reduced to stored genetic material and a fading chemical memory. What remains is responsibility without support, ambition without allies. In leafcutter ants, reproduction is not a personal milestone. It is a strategic expansion of territory carried out through biological warfare, environmental risk, and absolute commitment. The wedding is not the mating flight. It is the moment a queen breaks her wings and seals herself underground, choosing permanence over possibility. From that point forward, every success is magnified, every mistake irreversible. This is love as a founding act, stripped of sentiment and inflated to continental consequences. The forest floor does not record these events, but it bears their signature everywhere, in clipped leaves, altered soils, and the quiet hum of colonies that began with a single queen who survived when all others did not. Night settles heavily over the forest, thick with moisture and the low, fermenting scent of sap. Tree trunks glisten where bark has been wounded, oozing sugars that draw insects from wide radii. This is not a battlefield marked by sound or speed, but by mass and contact. On the vertical face of a tree, the arena is narrow, the footing uncertain, and the consequences absolute. For rhinoceros beetles, mating rights are not negotiated through displays or chemical persuasion. They are decided through leverage. Whoever can move the other body out of the way controls access. Romance here is mechanical. Male rhinoceros beetles arrive drawn by the same signal: sap flows that attract females seeking energy for egg production. The tree becomes a contested structure, its grooves and ridges defining the geometry of conflict. Males climb slowly, their heavy bodies adapted for pushing rather than pursuit. Each carries an exaggerated horn, a structure that looks ornamental until it is used. These horns vary in shape across species, forked or curved, but their function is consistent. They are not weapons designed to pierce or tear. They are tools built to lift, pry, and dislodge. When two males encounter one another near a feeding female, escalation is immediate. There is no prolonged assessment phase. Their sensory systems are tuned for close-range interaction, relying on tactile feedback and short-range chemical cues rather than vision. Compound eyes play a minimal role here. The environment is dark, cluttered, and static. What matters is grip. Claws hook into bark, legs brace. Bodies align perpendicular to gravity. The beetles lower their heads and engage horns, testing resistance like opposing levers pressed against the same fulcrum. The physics of the encounter favors size, but not indiscriminately. Larger males generate greater force, but only if they can anchor themselves effectively. Bark texture, moisture, and slope all influence outcomes. A smaller male with superior footing can resist longer, forcing the larger opponent to expend energy without progress. These contests can last minutes, an eternity for insects whose metabolic rates spike under exertion. Heat builds rapidly. As ectotherms, rhinoceros beetles depend on ambient temperature to sustain muscle performance. On cooler nights, fights slow, becoming grinding tests of endurance. On warmer nights, bursts of power decide outcomes quickly, favoring males with greater muscle mass and efficient energy storage. The goal is singular: removal. A successful male wedges his horn beneath his rival's thorax or abdomen and lifts, using the curvature of the horn to redirect force upward. Gravity does the rest. Once balance is compromised, recovery is nearly impossible. The displaced male scrabbles for purchase, legs scraping bark, but momentum carries him away from the sap flow. He falls, landing heavily on the forest floor below. Injury is possible, but not required. Displacement alone is defeat. Climbing back up costs time and energy, and by the time he returns, another challenger may have taken his place. What is striking is the restraint embedded in this violence. There is no biting, no tearing of soft tissue. Mandibles remain largely unused. The horn, despite its intimidating appearance, is not sharp. This minimizes the risk of fatal injury, allowing losers to survive and potentially compete elsewhere. From an evolutionary perspective, this matters. A system that kills competitors outright reduces the pool of viable males too quickly. By emphasizing displacement over destruction, rhinoceros beetles maintain competition while preserving population stability. Females, meanwhile, are not passive observers. They continue feeding, largely indifferent to the outcome until a clear winner emerges. Their interest aligns with efficiency. A male that can repeatedly defend a sap site demonstrate strength, stamina, and spatial control, traits that correlate with genetic quality. The female's choice is indirect, filtered through the outcome of physical contests rather than active selection. She mates with the male who remains, not because she evaluated his horn shape or color, but because he outlasted and outmoved all others. Predation pressure shapes these encounters subtly. Owls, mammals, and other nocturnal predators patrol the same trees, drawn by movement and scent. Prolonged battles increase exposure. This imposes a cost on excessive aggression. Males that escalate too often or linger too long become targets. Natural selection therefore favors decisive force applied efficiently. The best fighters are not those who fight most, but those who end fights quickly. There is also a developmental cost to bearing a horn. Producing such a structure requires significant resources during the larval stage, when beetles feed on decaying wood rich in nutrients. Larvae that fail to accumulate sufficient reserves develop smaller horns or none at all, adopting alternative strategies. These hornless males do not compete directly. Instead, they attempt to sneak matings by approaching females while dominant males are distracted. This polymorphism reveals an underappreciated aspect of rhinoceros beetle ecology. Brute force dominates, but only when resources allow it. When they do not, flexibility emerges. The bark arena itself becomes a selective landscape. Trees with extensive sap flows attract more beetles, increasing competition intensity. Those with limited flows host fewer encounters. Over time, this can influence mating success patterns across a forest, subtly shaping genetic distribution. The trees are not passive backdrops. They are structural determinants of reproductive outcomes, their injuries dictating where battles occur and how they unfold. Thermoregulation remains a constant constraint. Rhinoceros beetles are most active within specific temperature ranges, and mating seasons align with periods that support sustained muscular output. In cooler climates or seasons, reproductive activity compresses into brief windows, increasing competition density and raising the stakes of each encounter. In warmer regions, activity spreads out, allowing more opportunities and reducing the frequency of direct confrontation. Climate, therefore, modulates not only behavior, but the intensity of sexual selection. Once mating occurs, the victor's role ends quickly. There is no pair bonding, no guarding beyond immediate competition. The female departs to lay eggs in suitable substrates, often decaying wood that will nourish larvae for months. The male remains at the sap site, ready to defend again or be displaced in turn. Dominance is temporary, contingent on continued performance. Injury, fatigue, or the arrival of a larger rival can erase advantage in moments. Seen through a human lens, these encounters resemble a bouncer's work more than a duel. The objective is not to harm but to eject. Control the space, remove intruders, maintain access. It is an efficient system, brutally simple, stripped of nuance. Yet beneath that simplicity lies a network of ecological dependencies. Decaying wood availability determines larval success. Tree health influences sap production. Predator populations regulate beetle density. Each contest is a visible surface ripple on a deep, interconnected system. The rhinoceros beetle's wedding is not a singular event, but a repeated assertion of physical authority in a space defined by gravity and scarcity. Love is not expressed, it is enforced. Success is measured in seconds of dominance, earned through months or years of growth underground. Survival after victory is uncertain, but irrelevant to selection. What matters is that, for a brief window on a sap-streaked trunk, one male could lift another and send him falling away, securing a moment of reproductive access that will echo forward into the next generation. Dusk settles into the forest with a gradual cooling that changes the rules of movement. Heat stored in bark and soil bleeds away, and the air thickens with stillness. This is the hour when stag beetles emerge, climbing from leaf litter and rotting wood toward the vertical surfaces of trees. Sap flows glimmer faintly along fissured bark, marking feeding sites where females gather to replenish energy reserves. These locations become stages for a form of conflict that is both spectacular and tightly constrained, governed by physics, anatomy, and ritualized restraint. For stag beetles, marriage rights are not granted through persuasion or speed. They are seized through controlled force, executed with tools built not to kill, but to move other bodies out of the way. The male stag beetle's mandibles dominate his silhouette. Enlarged far beyond what is required for feeding, They curve forward like antlers, often serrated or branched depending on species. Their scale seems excessive until they are used. These structures are not adapted for biting flesh or tearing tissue. Their closing force is relatively modest compared to predatory insects. Instead, their shape and leverage are optimized for clamping around hard surfaces, locking onto an opponent's thorax or limbs, and lifting. The mandibles transform the male's head into a mechanical arm, capable of applying torque with surprising precision. When two males converge near a sap flow, the escalation follows a predictable sequence. They orient toward one another, raising their heads to display mandible size and spread. This visual assessment is not decorative. It allows each beetle to gauge the likely outcome before committing energy. Larger mandibles signal greater lifting capacity, and often greater body mass behind them. Many contests end here, resolved without contact as the smaller male retreats, conserving energy and avoiding injury. This restraint is not mercy, it is efficiency, shaped by selection to minimize unnecessary risk. When neither male yields, contact begins. They engage mandibles, interlocking like opposing hooks. The beetles brace themselves against the bark, legs splayed to maximize friction. The battle is slow, deliberate, almost silent. There is no flurry of motion, no rapid strikes. Instead, each male applies steady force, testing the other's grip and balance. Muscles contract under the constraints of an exoskeleton that limits flexibility but amplifies strength. The fight becomes a contest of leverage rather than speed. Gravity is the decisive ally. On a vertical trunk, losing balance is catastrophic. A beetle that is lifted even slightly off the bark loses traction instantly. Once a leg slips, recovery is nearly impossible. The victorious male uses his mandibles to lever the rival upward and outward, rotating him away from the tree. The fall that follows is not merely displacement. At insect scale, it is a knockout. The forest floor lies far below, and the time required to climb back up is significant. By the time the fallen male returns, the mating opportunity has passed, or another challenger has taken his place. This reliance on falling as defeat explains the evolutionary emphasis on lifting rather than biting. Inflicting injury would be costly and unnecessary. Removing a rival from the arena achieves the same result with less risk to both parties. The loser survives, but he is excluded. The winner retains access without compromising his own mobility. It is ritualized violence in its purest form, where form and function align to resolve conflict efficiently. Temperature plays a critical role in these encounters. Stag beetles are ectothermic, and their muscle performance depends on ambient warmth. As evening cools, muscle contraction slows, reducing lifting power and reaction speed. Fights early in the evening tend to be shorter and more decisive, while those later can become prolonged stalemates, each beetle struggling to generate sufficient force. This temporal gradient influences mating success, favoring males that arrive early or that possess greater thermal tolerance. The forest's microclimate, shaped by canopy cover and humidity, thus becomes an invisible participant in every duel. Females remain largely passive throughout these contests, continuing to feed while males battle nearby. Their presence is the incentive, not the judge. Selection occurs indirectly. A male that can secure and hold a sap site demonstrates not only physical strength, but persistence, spatial awareness, and the ability to manage energy expenditure. These traits correlate with larval development success, which depends on access to nutrient-rich decaying wood. The duel, therefore, reflects a lifetime of ecological conditions compressed into a single interaction. Predation risk imposes further constraints. Mammals, birds, and even large amphibians patrol tree trunks at night, drawn by movement and scent. Prolonged battles increase exposure. A male that escalates too frequently or fights too long becomes a target. This risk reinforces the value of dominance displays and early resolution. Winning quickly is safer than winning dramatically. Over time, this pressure has refined the stag beetle's combat style into something that looks ceremonial, but is underwritten by survival calculus. The mandibles themselves represent a developmental gamble. Producing such exaggerated structures requires significant resources during the larval stage. Larvae feed for years in decaying wood, accumulating energy that will later be allocated between body size, muscle mass, and mandible growth. Environmental variation during this period produces a spectrum of adult forms. Large males with massive mandibles dominate contests, while smaller males may adopt alternative tactics, avoiding direct confrontation and attempting to mate opportunistically when dominant males are distracted. This diversity of strategies reflects a balance between genetic potential and environmental constraint, ensuring that reproduction does not hinge on a single morphological outcome. The physics of these duels extends beyond individual bodies. Bark texture, moisture, and angle influence grip and leverage. Smooth bark reduces friction, favoring lighter males that can reposition quickly. Rough bark provides anchoring points that benefit heavier males capable of generating greater force. Sap itself can alter outcomes, making surfaces slippery and increasing the likelihood of accidental falls. Each tree presents a unique battlefield, and success in one location does not guarantee success in another. Once a male secures mating, his dominance is temporary. He does not guard the female beyond immediate competition. After mating, she departs to lay eggs in decaying wood, selecting sites that will support larval development for years. The male remains, ready to fight again or be displaced. Dominance must be continually reasserted. Injury, fatigue, or a change in environmental conditions can erase advantage quickly. The ritual repeats night after night until the breeding season ends or the male's reserves are exhausted. What distinguishes stag beetle combat is not its brutality, but its clarity. The rules are simple, enforced by gravity and anatomy. Lift, remove, replace. The mandibles, for all their size, rarely cause harm. They are instruments of control rather than destruction. This restraint allows populations to sustain intense competition without collapsing under excessive mortality. It is a system that channels aggression into predictable outcomes, maintaining stability, even as individuals clash repeatedly. At a broader ecological scale, these duels influence nutrient cycling and forest structure. By congregating at SAP sites, stag beetles concentrate feeding activity, accelerating decomposition and altering microbial communities. Their larvae break down wood that would otherwise persist, returning nutrients to the soil. The battles we see on the bark are surface manifestations of a deeper role, linking reproduction to ecosystem function. In the end, the stag beetle's wedding is less about pairing than about position. Marriage rights are secured through physical authority exercised within narrow bounds, shaped by evolutionary compromise. The violence is real, but it is measured, ritualized, and constrained by the costs of excess. Falling is defeat, remaining is victory, everything else is noise. The air above shallow water is never still. Even on windless days, heat rising from mud and vegetation creates invisible currents that fold and twist, shaping how insects move through space. Over ponds, ditches, and slow rivers, these currents form layered highways, and scarlet dragonflies patrol them relentlessly. Their red bodies flash against green reeds and dark water, not as decoration, but as territorial signals. In this environment, mating does not begin on a branch or leaf. It begins in motion, in contested airspace where every second counts and hesitation invites intrusion. Male scarlet dragonflies establish dominance by occupying stretches of air rather than physical structures. A sunlit patch of water, bordered by emergent plants, becomes a defended zone. From here, the male launches repeated patrols, tracing tight loops that skim the surface before rising sharply and turning back. These flights are not random. They maintain visibility while allowing rapid interception of intruders. The dragonfly's flight apparatus is among the most advanced in the insect world. 4 wings beat independently, enabling hovering, backward flight, and sudden lateral shifts. This control is essential because competition unfolds at speed. Females entering the area do so cautiously. Their arrival triggers an immediate response. The defending male accelerates toward her, closing distance in a fraction of a second. Contact must be precise. Using specialized claspers at the end of his abdomen, the male grips the female behind the head, locking her into a tandem position. This connection is mechanical and firm, designed to hold during sustained flight and abrupt maneuvers. There is no pause between capture and motion. Once locked, the pair takes to the air together, their combined mass altering flight dynamics but not slowing pursuit. This tandem flight is both courtship and defense. By physically attaching to the female, the male prevents immediate access by rivals. Yet attachment alone is not enough. Other males respond instantly, launching intercepts from nearby perches or entering from adjacent territories. The air fills with movement as challengers attempt to disrupt the pair. Chases are fast and aggressive. Rivals close in from behind or above, forcing the defending male to accelerate and maneuver while maintaining his grip. The energy cost is immense, but the alternative is loss. When the pair prepares to mate, their bodies fold into a wheel formation, one of the most precise mechanical alignments in insect reproduction. The female curves her abdomen forward to connect with the male's secondary genitalia, located not at the tip of his abdomen but beneath his thorax. This unusual arrangement requires flexibility, coordination, and stability in flight or while perched. The formation is brief because vulnerability peaks at this moment. While coupled, their ability to evade rivals diminishes. The surrounding airspace becomes dangerous. Rival males exploit this vulnerability. They attempt direct physical interference, ramming the pair or forcing separation through repeated passes. The defending male responds with relentless aggression, abandoning elegance for raw speed. Intercepts occur inches from the water's surface. Wings blur. The sound shifts from a steady hum to a sharp, rising buzz as acceleration peaks. These encounters are not symbolic. Contact can damage wings, and even minor tears reduce flight efficiency dramatically. In an animal whose survival depends on aerial control, such damage is often fatal. Thermoregulation shapes the tempo of these events. Scarlet dragonflies are heliothermic, absorbing heat from sunlight to elevate body temperature and power muscle performance. Mating activity intensifies during periods of direct sun, when wing muscles reach optimal operating temperature. In overcast conditions, activity slows, and territories expand as fewer individuals can sustain prolonged flight. Temperature thus governs not only physiology but social structure, determining how densely males compete and how frequently females are intercepted. Once mating concludes, the male does not release the female. Guarding continues. He remains attached or flies close above her as she moves to lay eggs, driving off rivals with repeated chases. This behavior reduces the risk of sperm competition, ensuring that his genetic contribution remains dominant. The guarding phase can last far longer than the act of mating itself, extending vulnerability and energy expenditure. The male's success depends on endurance as much as speed. Egg-laying sites introduce new hazards. Females deposit eggs on or just below the water surface, sometimes dipping their abdomens repeatedly while hovering. Predators lurk here. Fish strike from below. Frogs leap from the margins. Birds track movement from above. The guarding male must monitor threats in 3 dimensions, dividing attention between rivals and predators. His bright coloration, advantageous for signaling dominance, also increases visibility. The risk is constant. From an ecological perspective, this aerial violence shapes population structure. Dominant males monopolize high-quality territories, while subordinate males are pushed to marginal areas with fewer resources and lower mating success. This uneven distribution intensifies selection for flight performance, visual acuity, and aggressive responsiveness. Scarlet dragonflies possess large compound eyes that cover most of the head, providing nearly panoramic vision. This allows early detection of intruders and precise interception trajectories, even at high speed. The energy demands of this system are enormous. Dragonflies are apex insect predators, consuming mosquitoes, flies, and other small insects in flight. High caloric intake fuels reproductive aggression. When prey availability drops, territorial intensity declines. Males patrol less, conflicts shorten, and females encounter fewer intercepts. Thus, mating behavior is tightly coupled to broader food web dynamics. A surge in prey populations can indirectly amplify reproductive violence by enabling longer and more frequent aerial engagements. Despite the chaos, the system is highly efficient. Mating is fast, guarding is decisive, and resolution occurs quickly. There are no prolonged stalemates. The moment a rival proves superior in speed or endurance, displacement follows. The loser retreats, conserving energy for another opportunity elsewhere. Injury is costly and usually avoided through disengagement rather than escalation beyond control. What distinguishes scarlet dragonfly reproduction from ground-based contests is its immediacy. There is no buffer between interaction and consequence. Mistakes are punished instantly by gravity, predators, or rivals. The air offers no refuge. Every movement is exposed, every pause exploited. The violence is not dramatic in duration, but it is relentless in frequency. Throughout the breeding season, these encounters repeat thousands of times, each one shaping the genetic future of the population. Viewed through this lens, mating is not a separate behavior layered onto daily life. It is inseparable from survival. Flight performance, feeding efficiency, predator avoidance, and reproduction all draw from the same physiological budget. Success in one domain reinforces the others. Failure cascades rapidly. The scarlet dragonfly's wedding is not marked by ceremony or stillness. It is marked by speed, contact, and constant interference. Precision replaces patience. Control replaces choice. In this system, love is not an exchange between individuals, but a sustained act of dominance in contested airspace. The wheel formation, elegant and brief, is the eye of the storm. Around it, the air remains crowded, hostile, and unforgiving. When the season ends and temperatures fall, the air quiets. Territories dissolve. The survivors disperse. What remains is the legacy of countless aerial confrontations, encoded in the next generation of larvae, hidden beneath the water's surface. The violence fades, but its consequences endure, carried forward by bodies built to fly fast, see everything, and never hesitate when another shape enters the sky. The heat presses down on the landscape until even the air seems reluctant to move. Trees stand heavy with summer, their leaves holding sunlight like stored fuel. In this stillness, the first cicada call breaks the silence, sharp and mechanical, a sound that feels less like a voice and more like a force. It vibrates through bark and bone, announcing not just presence, but readiness. In cicadas, romance does not whisper. It overwhelms. Mating begins as an acoustic escalation, where survival, visibility, and desire collide in a chorus that can dominate entire ecosystems. Male cicadas are built to be heard. Their bodies house tymbals, ribbed membranes on the abdomen that buckle inward and snap back with astonishing speed. Each contraction produces a click, and thousands of clicks merge into a sustained call that can reach volumes rivaling industrial machinery. This is not incidental noise. It is a precisely tuned biological instrument, amplified by hollow abdominal cavities that function as resonance chambers. Evolution has shaped these insects into living loudspeakers, optimized to project sound across dense vegetation where visual signals would fail. The purpose of the call is simple in theory and complex in execution. Females listen. They do not respond to any call, but to specific patterns embedded within the noise. Frequency, rhythm, duration, and timing all matter. A call that is too weak is lost in the background. A call that is mistimed is ignored. A call that deviates subtly from species-specific parameters fails entirely. The male's song carries information about his size, health, and stamina. Only individuals with well-developed musculature, intact tymbals, and sufficient energy reserves can sustain the most attractive calls for extended periods. Once a male begins calling, others join. What starts as a solitary signal rapidly escalates into a chorus. Trees become acoustic arenas, each branch hosting multiple males competing for auditory dominance. The air fills with layered frequencies that overlap and interfere, creating a shifting soundscape where individual calls struggle to remain distinct. In this environment, competition intensifies. Males adjust timing to avoid overlap, inserting their calls into brief gaps. Others increase volume, pushing their muscles to the limit. Endurance becomes a weapon. The longest, loudest callers gain the greatest chance of being heard by receptive females. This is not a cooperative choir. It is a battlefield shaped by sound. Calling requires enormous energy. Muscle contractions occur at rapid rates, generating heat and metabolic stress. Cicadas must manage thermoregulation carefully, positioning themselves to dissipate heat through airflow or shaded surfaces. In extreme heat, calling becomes dangerous, risking overheating and muscle failure. Yet silence guarantees reproductive failure. Males walk a narrow physiological margin, balancing performance against collapse. Females navigate this acoustic chaos with precision. They move toward preferred calls, guided by subtle differences in intensity and pattern. Their auditory systems are finely tuned, capable of discriminating between nearly identical signals amid overwhelming noise. When a female selects a male, she responds with wing flicks or brief movements that signal her location. The successful male breaks from the chorus, moving toward her, while others continue calling, unaware that one competitor has exited the contest entirely. But the chorus carries far beyond its intended audience. Predators hear it too. Birds, bats, and parasitic flies exploit cicada calls as beacons. For them, the sound is not romance, but opportunity. Some predators have evolved auditory systems tuned specifically to cicada frequencies, allowing them to home in on calling males with lethal accuracy. Parasitic flies take this a step further, depositing larvae on or near the calling cicada. These larvae burrow into the host, consuming it from within. The very trait that attracts mates also invites death. This risk is not theoretical. Mortality rates among calling males are high. Each sustained call increases exposure, extending the window during which predators can triangulate position. Silence reduces risk, but eliminates reproductive chance. Natural selection has not resolved this conflict by softening the call. It has resolved it by demanding efficiency. Males that can call loudly and successfully within shorter time frames reduce exposure while maintaining attractiveness. Timing matters. Calling peaks during specific hours when predator activity is lower or environmental conditions dampen detection. Even then, danger remains constant. The ecological consequences of these choruses ripple outward. Cicadas often emerge in synchronized broods, flooding ecosystems with biomass. Their calls dominate soundscapes, altering predator behavior and even influencing human perception of seasonal change. When they die, their bodies enrich the soil, transferring nutrients from canopy to ground. Trees respond with increased growth. The mating chorus is thus not only a reproductive event, but a driver of nutrient cycling and forest dynamics. Physiology underpins every aspect of this system. Cicadas are ectothermic, and their calling performance is temperature-dependent. Warmer conditions increase muscle efficiency, allowing faster timbal contractions and louder calls. Cooler temperatures slow activity, compressing calling into brief, intense bursts. Climate patterns therefore shape reproductive success across years, influencing which males are heard and which remain silent. Despite the overwhelming noise, there is order within the chaos. Each species occupies a specific acoustic niche, minimizing interference with others. Frequencies differ slightly. Rhythms vary. This partitioning allows multiple species to call simultaneously without complete signal loss. It is an evolutionary compromise that maintains diversity within crowded soundscapes. The irony is stark. Cicadas invest everything in a signal that shortens their lives. Many species live underground as nymphs for years, feeding on root sap, growing slowly and invisibly. When they finally emerge, adulthood is brief. Weeks, sometimes days. That time is spent almost entirely calling, mating, and avoiding predation. There is no recovery phase, no prolonged partnership. The song is the life. In this context, romance is not a bond but a broadcast. The male does not court a specific female until the moment of selection. He sends his signal into the environment and accepts whatever outcome follows. Success means mating and continuation of the lineage. Failure means silence, starvation, or predation. The system is unforgiving but efficient. It ensures that only individuals capable of sustaining extreme physiological output contribute to the next generation. As dusk approaches and temperatures drop, the chorus shifts. Some males fall silent, muscles spent. Others persist, voices rasping but determined. Predators adjust, moving toward the remaining signals. The soundscape thins, but it does not disappear. Somewhere in the trees, a female responds, drawn to a call that cut through the noise at exactly the right moment. The forest absorbs the sound without judgment. Leaves vibrate. Bark resonates. The chorus fades and swells again, indifferent to individual fates. Romance here is not private or gentle. It is a public risk shouted into the world, where every love song is also a flare announcing position to anyone listening. The meadow looks gentle from a distance, washed in pale light and drifting pollen, a place where motion appears unhurried and fragile. Monarch butterflies move through this space like fragments of color, their wings flashing orange and black as they rise and settle among milkweed and wildflowers. The scene suggests delicacy, even vulnerability. Yet beneath this softness lies a system shaped by pressure, constraint, and calculation. In monarchs, mating is not a calm interlude between migrations. It is a costly transaction conducted under the shadow of depletion, where control and competition are woven into behaviors that appear effortless only because evolution has hidden the force behind them. Courtship begins in the air. Males patrol open spaces and nectar-rich corridors, scanning for the distinctive flight pattern of females. Vision plays a central role here. Monarch eyes are tuned to detect movement and color contrast against vegetation and sky, allowing males to identify conspecifics at distance. When a female is spotted, the male accelerates, closing the gap through sustained flight that tests endurance as much as speed. This pursuit is not a display meant to impress from afar. It is an interception strategy. The male must position himself precisely, matching the female's altitude and trajectory, while compensating for wind and thermal currents that buffet lightweight wings. Chemical communication overlays this visual pursuit. Males release pheromones from specialized scales, broadcasting their presence and condition. These chemicals are not perfumes in a romantic sense. They are signals shaped by metabolism, reflecting diet, health, and age. Females detect these cues with remarkable sensitivity, integrating them with visual and tactile information as the chase unfolds. A male that cannot sustain flight long enough to maintain proximity will not be evaluated further. Endurance is the first filter. When contact is made, the interaction becomes physical. The male attempts to force the female to the ground or into vegetation where mating can occur. This is not a gentle landing. It often involves grappling mid-air, wings colliding, bodies twisting as gravity pulls both downward. Control is essential. The male must position himself to prevent escape while avoiding damage to wings that are critical for future movement. The female resists, not passively, but through active flight and maneuvering. This resistance is part of selection. Only males capable of maintaining control without catastrophic loss succeed. Competition intensifies when multiple males converge on a single female. What might appear from a distance as a chaotic swirl is in fact a layered contest of positioning, interference, and timing. Males bump, block, and displace one another, using their bodies rather than specialized weapons. There is no horn or mandible here, but force is applied nonetheless, through mass, wing beat strength, and spatial awareness. A male that loses altitude or momentum is quickly excluded, falling behind as others close in. These contests are brief but decisive, resolved in seconds that determine reproductive success. Once mating begins, the male maintains physical control, often holding the female in place for extended periods. This guarding behavior reduces the likelihood of rival interference and subsequent mating attempts. The cost is energy. Monarchs operate on tight budgets. Every gram of lipids stored in the abdomen represents flight distance, thermal buffering, and survival capacity. Prolonged mating and guarding deplete these reserves, forcing a trade-off between reproductive investment and future viability. This trade-off becomes stark when viewed through the lens of migration. Monarch butterflies are renowned for long-distance movement, traversing entire continents to reach overwintering sites. These journeys are fueled by stored energy accumulated through feeding. Calories are not abstract units. They are wing beats, kilometers, days of sustained flight. Mating occurs within this framework. Love is expensive, because it consumes the same currency required for migration. Timing matters. Monarchs that mate too early risk depleting reserves before migration begins. Those that delay may miss opportunities altogether. Environmental cues such as day length, temperature, and nectar availability shape these decisions, influencing when individuals prioritize reproduction over movement. Thermoregulation plays a critical role. Monarchs bask to raise body temperature before flight, absorbing solar radiation through dark wing veins. This behavior conserves energy but increases exposure to predators. Every choice carries layered consequences. Predators are constant participants in these encounters. Birds watch open fields, tracking erratic flight patterns that signal pursuit or struggle. A mating pair descending into vegetation may evade immediate detection, but prolonged activity increases risk. The very act of competition draws attention. In this sense, mating amplifies vulnerability, turning reproduction into a calculated gamble against predation. The ecological context extends beyond individual butterflies. Milkweed availability determines larval success, shaping population density and adult competition. Nectar abundance influences adult condition, affecting flight endurance and pheromone production. Climate variability alters flowering schedules and migratory timing, cascading into mating dynamics. A drought year compresses resources, intensifying competition and raising the cost of each mating attempt. A favorable year spreads opportunity, softening conflict, but never eliminating it. What is often overlooked is the physical toll of mating on females. Carrying a male during prolonged coupling adds weight and alters flight mechanics, increasing energy expenditure and reducing maneuverability. This cost influences female choice indirectly. Resisting weaker males minimizes unnecessary depletion, preserving reserves for egg production and migration. Selection thus operates through both acceptance and avoidance, sculpting behaviors that appear subtle but are grounded in physiological accounting. The softness of monarch wings belies their resilience. Scales flake and edges fray over time, evidence of battles survived and distances covered. A heavily worn butterfly carries a history of choices etched into its body. Each mating, each escape, each long flight leaves a mark. Survival is cumulative, not guaranteed. Individuals that misjudge their energy budgets pay later, often far from the scene of courtship. From an evolutionary perspective, this system balances beauty and brutality. Monarch mating lacks the overt violence of beetle duels or the fatal consequences of bee reproduction, yet it is no less demanding. Control replaces combat, endurance replaces force, but the stakes remain high. Genes move forward only if bodies can afford the cost. As migration resumes, many monarchs leave mating grounds carrying the consequences of earlier decisions. Those that invested heavily may struggle to complete the journey. Others, leaner but unmated, gamble on opportunities later along the route. The population spreads across landscapes, each individual a node in a vast moving network shaped by weather, plants, and predators. The meadow returns to its quiet rhythm. Wings drift, flowers sway, and the scene regains its softness. But beneath this calm lies a record of exertion and risk. The monarch's wedding is not fragile. It is disciplined, strategic, and constrained by the unforgiving arithmetic of energy. Love here does not float free of survival. It is weighed, measured, and paid for in calories, distance, and time. The forest understory exists in a perpetual half-light, a place where sunlight filters through layers of leaves and arrives already softened, fragmented into moving patterns that never fully settle. In this dim world, visibility is unreliable, shapes blur, depth is deceptive. It is here, beneath the canopy, that owl butterflies conduct their courtship, relying not on speed or sound, but on illusion. Their wings carry enormous eye spots that seem almost excessive, dark circles ringed with yellow and white that stare back at anything close enough to notice. These markings are famous for their role in predator deterrence, but they also shape the most consequential interactions of all. In owl butterflies, beauty is not ornamental. It is a tool calibrated for survival and reproduction in equal measure. Courtship unfolds slowly, often beginning with stillness. A male perches on a trunk or broad leaf, wings closed, eye spots concealed. When a female passes through the understory, he opens his wings deliberately, revealing the full pattern in a sudden, controlled display. The contrast is striking even in low light. The eye spots appear almost three-dimensional, amplified by subtle wing movements that catch what little light penetrates the forest. This is not random signaling. Timing and angle matter. The display must be seen clearly enough to register, but not so abruptly that it startles the observer into flight. Females assess these displays with more than aesthetic judgment. The symmetry, clarity, and contrast of the eye spots provide information about the male's developmental history. Producing precise wing patterns requires stable conditions during metamorphosis, adequate nutrition, and resistance to disease. Even minor disruptions can distort symmetry or dull coloration. The wings become records of past success, encoding environmental resilience into visible form. In this way, visual beauty becomes a proxy for genetic quality. But the forest is not empty. Other males watch, and the moment a display draws attention, competition intensifies. Rival males intercept flight paths, positioning themselves between the displaying male and the female. These interactions are subtle but forceful. Blocking does not require contact. By occupying critical airspace, a rival can disrupt approach angles, forcing detours that sap energy and break visual continuity. In the understory, where navigation depends on maintaining orientation among vertical trunks and shifting shadows, even small disruptions matter. When blocking fails, chases begin. Owl butterflies are not fast compared to open sky species, but within their environment, maneuverability is key. Broad wings allow controlled gliding and sharp turns, enabling pursuit through cluttered vegetation. Chases weave around trunks and under leaves, each participant exploiting familiarity with microhabitats. These pursuits are less about catching than exhausting. The male that forces the other into prolonged flight gains an advantage because energy reserves here are limited. Thermoregulation shapes every movement. Owl butterflies are ectothermic, relying on ambient warmth to power flight muscles. In the understory, temperatures fluctuate less dramatically than in open fields, but they are often cooler. Butterflies must bask strategically, angling wings to capture stray sunbeams before flight. A male that enters a chase without sufficient warmth risks rapid fatigue. Competition therefore favors individuals that manage their thermal state effectively, balancing exposure to predators against the need for muscular readiness. Predators are never absent from this equation. Birds hunting by sight patrol the same spaces, and the eye spots that intimidate predators during rest can attract attention during flight. When a butterfly flashes its wings mid-chase, it risks drawing the gaze of something larger and faster. The eye spots function as both shield and signal, deterring some attacks while increasing visibility. This duality adds complexity to courtship. Displays must be compelling enough to attract mates, yet restrained enough to avoid lethal attention. Physical contact does occur, though rarely with the violence seen in beetles or dragonflies. Males bump rivals deliberately, using wing edges to destabilize flight. These collisions are controlled, avoiding damage to wings that would compromise future survival. The goal is displacement, rather than injury. Forcing a rival to retreat or land ends the contest effectively, allowing the victor to resume display without immediate interference. Females navigate this chaos with caution. Their role is not passive. By altering flight height, speed, or direction, they can test male persistence and adaptability. A male that maintains position despite obstacles demonstrates both endurance and spatial awareness. Selection here operates through prolonged assessment rather than immediate victory. The process favors consistency over aggression, control over speed. Once a female accepts a male, mating occurs on a perch, often concealed beneath leaves or against tree bark. Even here, vigilance remains high. Rival males may attempt interference, and the mating pair must remain alert to predators. The act itself is relatively brief, but its timing is critical. Energy expended during competition must leave enough reserve for subsequent survival, and for females, egg production. The ecological context extends beyond individual interactions. Owl butterflies often inhabit stable forest environments where resource availability fluctuates less dramatically than in open landscapes. This stability supports prolonged adult lifespans, allowing multiple mating opportunities, yet it also means competition accumulates over time. Males encounter the same rivals repeatedly, learning patterns of movement and preferred perches. Subtle advantages compound, shaping dominance hierarchies that persist across days or weeks. Wing patterning plays another role here, influencing not only mate choice, but rival assessment. Males with more pronounced eye spots are often avoided by competitors, reducing the frequency of direct confrontation. This avoidance is not conscious, but it emerges through selection. Rivals that challenge dominant-looking males incur higher costs with lower success rates. Over time, strategies shift toward exploiting moments of distraction rather than frontal competition. The irony is that these eye spots evolve primarily to deceive predators, mimicking the gaze of larger animals to trigger hesitation. In the mating arena, the same deception influences insects capable of learning and memory. The boundary between predator deterrence and sexual signaling blurs, revealing how traits shaped for one purpose can be co-opted for another. Beauty in this sense is layered. It operates simultaneously on multiple audiences, each interpreting the signal differently. Energy budgeting remains the underlying constraint. Every display, chase, and confrontation consumes reserves that must sustain the butterfly through rest, feeding, and future encounters. Nectar intake replenishes some of this energy, but feeding exposes butterflies to predators and limits time available for courtship. Choices must be made continuously. A male that displays too often risks exhaustion. One that conserves energy may miss critical opportunities. As seasons progress and conditions change, these dynamics shift subtly. Increased humidity affects wing performance. Reduced sunlight limits basking opportunities. Population density fluctuates with resource availability. Each factor alters the balance between display and competition, reshaping the mating landscape without changing its fundamental rules. In the end, owl-butterfly courtship reveals a central truth of insect reproduction. Even in systems that appear gentle, conflict is present, embedded in movement, positioning, and endurance rather than overt violence. Patterning is not passive decoration. It is a signal forged by survival, refined by competition, and deployed strategically. The forest understory returns to quiet as individuals disperse. Wings fold, eye spots disappear into camouflage. Yet the outcomes of these encounters persist, encoded in eggs laid on host plants and in the genetic makeup of the next generation. Beauty here is never neutral. It influences who is seen, who is avoided, and who succeeds. In the insect world, aesthetics and aggression are inseparable, and every display carries the weight of selection. What looks like art is, in truth, a weapon wielded in the marriage market, sharpened by evolution and tested in shadowed air.